Hello, good morning. This is Jayalakshmi of IK College of Engineering. Today we are going to discuss about that second video in that first unit of EC8652, that is wireless communication. We are going to discuss about that path class model, small scale fading and large scale fading. In that one we are going to discuss about path class model. Let me start with that introduction to radio wave propagation. The mobile radio channel places fundamental limitations on the performance of wireless communication. The paths can vary from simple line of sight to ones that are severely obstructed by buildings, mountains and foliage. So radio wave channels are extremely random and difficult to analyze. The speed of the motion also impacts how rapidly the signal level fades as mobile terminals moves about. Basics of propagation. When we are going for that, when a wave is transmitted, that is radio wave is transmitted from one terminal to another terminal at very low frequency and low frequency and medium frequency bands, radio waves follow the ground, and AM radio broadcasting uses this middle frequency range. When you are going for that high frequency range, that the ground waves tend to be absorbed by the earth. The waves that reach ionosphere, that is 100 to 500 km above the earth's surface, are refracted and sent back to the earth. Due to that one, there will be some variation in the received signal. When you are going for that very high frequency range, there will be a directional antennas. If you are using directional antennas, then we will have a line of sight path as well as a reflected wave path. So when we are receiving that at the receiver end, we will have some interference, that is we will have some losses in the signal strength. What all the problems you are facing uniquely in wireless system are interference from other service providers and interference from other users in the same network, co-channel interference due to frequency reuse, or other channel additional channel interference when you are going for that one, and the transmitter receiver design limitations, and large users sharing when they are sharing that finite bandwidth, we are having that interference problem. And then shadowing, obstruction to line of sight paths causes areas of weak received signal strength. Then fading. When no clear line of sight path exists, signals are received that are reflection of obstructions and diffraction around an obstruction. Multipath signals can be received that interfere with each other. Then fixed wireless channel, random and unpredictable fading happens. This must be characterized in a statistical fashion. Field measurements often needs to be characterized radio channel performance also. So fading is another one important problem when you are going for wireless communication. Then mechanism that affect the radio wave propagation: reflection, diffraction, scattering. In urban area, there is no direct line of sight path between the transmitter and the receiver, and there will be the presence of high-rise building that causes severe diffraction losses. Multiple reflection cause multipath fading also. What is reflection? Reflection arises when the plane waves are incident upon a surface with dimensions that are very large compared to the wavelength. When you are going for the diffraction occurs according to Huygens principle when there is an obstruction between the transmitter and receiver antenna, and secondary waves are generated behind the obstructing body. And then finally scattering occurs when the plane waves are incident upon an object whose dimensions are on the order of the wavelength, or it is less, and this causes the energy to be redirected in many directions. This figure shows that what happened when you are having that reflection, refraction and diffraction. When you are transmitting a data, due to that buildings, there will be a reflection and there will be a scattering and diffractions. Here when you are discussing about that one, if you are near to that antennas, then you will have that line of sight. When you are going out far from that antennas, then when there is an obstacles, that is large buildings like that one, then we will have that reflection, diffraction and scattering. As a mobile moves through a coverage area, these three mechanisms have an impact on the instantaneous received signal strength. If a mobile does have a clear line of sight path to the base station, then the diffraction and scattering will dominate the propagation. So when we are having the clear line of sight path, then you won't have any loss in that one. If a mobile is at a street level without line of sight, then the diffraction scattering will probably dominate the propagation. That time you will have that signal loss. As the mobile moves over small distances, the instantaneous received signal will fluctuate rapidly, giving rise to the small scale fading. That is, the reason is that the signal is the sum of many contributors coming from different directions, and since the phases of these signals are random, the sum behave like a noise. Okay, that is explained in relay fading. In small scale fading, the received signal power may change as much as 3 to 4 order of the magnitude when the receiver is only moved a fraction of the wavelength. As the mobile moves away from the transmitter over larger distance, the local coverage received signal will gradually decrease. This is called as large scale path loss, and we are going to discuss about that large scale path loss models, the models that predict the mean signal strength for an arbitrary transmitter receiver separation distance and are called large scale propagation models. They are useful to estimate the coverage area of a transmitter. Let me start with free space propagation model. The free space propagation model is used to predict received signal strength when the transmitter and receiver have a clear, unobstructed line of sight path between them. For example, satellite communication systems and microwave line of sight radio links typically undergoes this free space propagation. As the most large scale radio wave propagation models, the free space propagation model predicts that received power covered function for the transmitter receiver. The free space propagation model, the free space power received by the receiver antenna, which is separated from a radiating transmitter antenna by a distance d, is given by the free space equation, and with that power transmitter, PT as a power transmitter, PR as the received power. Then we are having this one, the PT as that is the received power PR as given as PT into GT into GR into lambda square divided by 4 pi squared d square. Okay, into d square divided by PT into GT into GR into d square divided by 4 pi square lambda square. Okay, here that PR is the received signal power and PT is the transmitted signal power, and GT and GR as the gain of the antennas, and lambda is the wavelength, and L is the loss, and D is the distance separation between the transmitter and receiver. When you are going for that free space propagation model, the gain of the antenna related to its effective aperture AE by that AE, and there will be a the effective aperture is related to the physical size of the antenna, and lambda is related to the carrier frequency. Okay, here that the carrier frequency can be given by F by C. Carrier frequency can be given by lambda by omega C, and that C is the speed of the light. The received power decays with the distance at a rate of 20 dB per decade, and isotropic radiator is an ideal antenna which radiates power with unit gain uniformly in all directions, and is often used to reference antenna gains in the wireless system, and that is given by EI. The effective isotropic radiated power is defined by ARP equal to PT into GT. Then in practice, the effective radiated power is used instead of EARP to denote that maximum radiated power as compared to a half wave dipole antenna. Instead of that isotropic antenna, dipole antenna is used. That time we are going for EARP. The EARP will be 2.15 dB smaller than that EARP for the same transmission system. In practice, antenna gains are given in units, that is dB, dB gain with respect to an isotropic source, or dBd with respect to half-wave dipole antenna. The path loss, which represents signal attenuation as a positive quantity measured in dB, is defined as the difference between the effective transmitted power and the received power, and may or may not include the effect of antenna gains. The path loss for the free space model with antenna gains are included, given by path loss in dB is given by 10 log power transmitted divided by power received, that is minus 10 log GT GR lambda square divided by 4 pi square D square. Fraunhofer region of a transmitting antenna is defined as the region beyond the far field distance d1, which is related to the largest linear distortion, dimension of the transmitter antenna aperture and the carrier wavelength. That is, df is given by 2d squared by lambda, where df is greater than the distance, where d is the largest physical linear dimension of the antenna, additional to the df is greater than d, and and d1 must satisfy, additional to df is given as 2d squared by lambda, and the far field d1 must satisfy df is greater than dd, and the received power is given as power pd, and that is received power pr in d is given by transmitted power plus, that is received power pr d in dBm is equal to 10 log pr d naught divided by 0.001 w plus 20 log d naught by d. Here is some example problems for that received power calculation using free space propagation model. Okay, and then within that we have completed the free space propagation model. In next video we will start with ground reflection model.